Very good afternoon to one and all, and welcome you all in the next lecture of heat transfer. Whether my voice is audible and can you see my presentation? Please let me know. Comment in the chat box, and please adjust your screen according to uh, your requirement. Yes, thank you, thank you. Great. Please adjust your screen. You can rotate your screen and you can use the zoom feature so that it will be more visible and you will see all the points clearly from the Word file. Okay, so in the last lecture, we have discussed about the convection. Okay, what is meant by convection and the Newton's law of cooling governing the convection, then the convective heat transfer coefficient, and the convective dependency of convective heat transfer on the fluid properties such like thermodynamic and transport properties such as uh, uh, thermal conductivity, specific heat, kinematic viscosity, dynamic viscosity, then fluid flow condition like laminar flow, turbulent flow, then transition flow, then the temperature conditions like the temperatures of surface and the fluid and its difference, then geometric condition whether the system is plane wall, the system is cylinder, or the system is sphere. So on various conditions, this particular H factor depend. That is nothing but convective heat transfer coefficient factor depend. Okay. Then we have discussed further about uh, uh, about the two different problems of convective heat transfer about the convection. Okay, and also we have discussed the electrical analogy for the Newton's law of cooling, and from that we will get the thermal resistance offered for the heat transfer in a convection heat transfer mode. Okay, so that we have discussed in the last lecture. So in the introduction point, the last point of a discussion is nothing but a radiation. Okay, this is the third mode of a heat transfer, that is nothing but radiation. There are three modes of a heat, basic three modes of a heat transfer, that is conduction, convection, and radiation. So from that three modes we have discussed about the two modes, that is first one is a conduction, second one is a convection, and the last and not the least, that is the radiation. Okay, so we know that our mother earth on our mother earth, the most of the energy source, or we can say that the most important energy source is the sun, and which is far away from the mother earth. Okay, so which is so far away from the mother earth, then also we receive the abundant amount of energy from the sun. Okay, we receive abundant amount of energy from the sun, and because of that there is a living species, or we can say that we are living on the earth because of the sun only, because it is the only one source available for the mother earth. Okay, energy source available for the mother earth. Okay, and due to that source only we are living on this particular planet. Okay, now how the energy is transferred from sun to earth, because there is no medium present in between sun and earth. There is no medium in between sun and earth, only space, only vacuum is available. Okay, means what? There is no medium, there is no atmosphere in between sun and earth. You can see that only near about we can say that near about 50 kilometer away from the ground there is atmosphere, and afterward there is space only. Okay, and there is no any medium present in between sun and earth. Then also we are receiving the energy from sun. Okay, why it is happening that there is no any source? between sun and there is no any medium in between sun and earth, then also why we are receiving the energy from sun? Because this kind of energy which are we are receiving, this energy type is called as a radiation energy, or this energy transfer from sun to the earth is called as a radiation heat transfer, is called as a radiation heat transfer. Okay, so remember one thing, important point about the radiation. Remember this particular point. Everybody, okay, every living, non-living, everybody, okay, in fact the eyes also, okay, everybody emit radiation in every direction. Okay, everybody emit radiation in every direction except 0 Kelvin temperature, except 0 Kelvin temperature. 0 Kelvin temperature means what is the significance of a Kelvin temperature? 0 Kelvin means minus 273 degrees Celsius temperature. 0 Kelvin means minus 273 degrees Celsius. Okay, so below that particular temperature, body stop to emit the radiation. But uh, if the body temperature is above 0 Kelvin, that is above minus 273 degrees Celsius temperature, then that particular body also emit the radiation. Okay, no matter it is a living organism or a living entity or the non-living entity, but everybody emits radiation in every direction. Okay, remember this point. Okay, then why the radiations are traveled through vacuum? Okay, or how it the heat by radiation is transforming in the vacuum? Because we know that the light medium, okay, or light does not require any medium to propagate, okay, or to travel. Okay, it can also travel through vacuum also. Okay, it can also travel through vacuum. Okay, in a similar manner, this light rays or whatever the light rays are there, with that particular light rays, electromagnetic waves are also propagating. Okay, electromagnetic waves are also propagating with the speed of a light, okay, and these electromagnetic waves, where they will strike, they will release the energy, or they will release the heat energy at that particular place. Okay, where they strike, where they bombard, they will that particular electromagnetic waves emit the energy to that particular surface. Okay, and that energy release will be happen in a quantum. We know the quantum theory. So in a quantum, energy will be released. Okay, so because of this particular feature, radiation heat transfer does not require any kind of a medium. Okay, because of this feature, the radiation heat transfer does not require any kind of a medium. Okay, so they can travel with in a vacuum also. They can travel in an atmosphere where in a space where the atmosphere is present. Okay, so we can say that all the bodies above above the temperature of 0 Kelvin emits radiation. All the bodies above 0 Kelvin temperature emits the radiation. Okay, so radiation heat is a thought of an electromagnetic waves. Okay, radiation heat is a thought of an electromagnetic waves. So heat transfer, so transfer of heat by radiation occurs because hot body emits more heat than it receives, and cold body receives more heat than it emits. Okay, what is the meaning of this particular sentence? Okay, now you are saying that everybody emits radiation, then who will receive this particular emitted radiations? So remember one point, that everybody emits radiation, it is true. Okay, but that particular body also receives the heat. Okay, or that particular body also receives the radiation from another body. Okay, so in such a manner, the radiation heat will transfer from one body to another body. Okay, but more important thing is that then who will be the more receiver and who will be the more acceptor? Okay, So this is the difference between two bodies, or it is important to attain the equilibrium. Okay, one can say it is important thing to attain the equilibrium. Equilibrium will be attained in between two bodies when the temperature of two bodies will be same one. In that case, that particular two bodies will emit the radiation. Same amount of radiation will be emitted by particular bodies, and same amount of radiation will be received by that particular bodies. Okay, remember this thing. If two bodies having different temperature, okay, which are not at a equilibrium state, and not at a equilibrium state means what? Both the bodies having different temperature. One is hotter one and one is cooler one. Okay, let us consider one is hotter one and one is cooler one. So in that case also, hotter body emit the radiation, cooler body also emit the radiation, but the rate of emission of a radiation is more from the hot body, and whereas the rate of emission of radiation from cooler body is less as compared to the hot body. Okay, whereas in another sentence we can say that less amount of heat will be received by hot body, whereas more amount of heat will be received by the cold body because of a radiation heat transfer. Because of a radiation heat transfer. Getting this point? Getting this point, everyone? Clear this point? Okay. Everybody emit radiation. Okay. If you consider that there are two bodies, and one is the hot body, and one is a cold body. So in that case, hot body will emit more radiation, okay, and receive less radiation from the cold body, whereas cold body receives more radiation, or the more heat by radiation from the hot body, and will emit less heat towards the hot body, and this will happen up to what point? When they will reach to equilibrium state. That is nothing but what? Their thermal temperature, or temperature of two bodies, will be equal. At that time, the rate of emission is equal to the rate of receive. Okay, rate of emission of radiation of a particular body is equal to the rate of receive of radiation of that particular body. Okay, of that particular body. Getting this particular point? So transfer of heat by radiation occurs because hot body emits more heat than it receives, and cold body receive more heat than it emits. Okay, and as we have discussed, the radiation heat transfer does not require any medium. Okay, so requires no medium for the propagation, will pass through vacuum. Also, the important point is it travel with the velocity of a light. So velocity of light is how much? 3 into 10 raised to 3 meter per second, right? Or wrong? 3 into 10 raised to 3 meter per second. It is the velocity, or kilometer per second? So let me know. What is the velocity of light? Okay, you think about that. So it travels with velocity of light. Okay, as the light follows some kind of phenomena like interference, diffraction, polarization, same kind of a phenomena will be followed by the radiation. So like light, it shows interference. Okay, like light, it shows interference, diffraction, polarization, etc. Then radiation heat can be reflected. Okay, as the light rays are reflected in a similar fashion, radiant heat can, or radiations can be reflected from the surface and obeys the ordinary laws of a reflection. Okay, so we can say that whatever the laws we are applying for the light, we have discussed about the interference in the physics, then diffraction, then polarization. Same kinds of phenomena can be observed by the for the radiation waves, or for the radiation, and it also shows the laws of a reflection. Okay, so incident ray, reflected ray, angle made by in between the normal. So all these particular points we are going to discuss in the radiation chapter. But here you have to remember that the radiation heat, or the radiations, are following all the laws related to the heat, or the laws related to the light. Okay, all the laws related to the light. Okay, now which law is governing the radiation? Okay, So there are many laws. Okay, Kelvin law, then cosine rule. There are many laws about the radiation, but the basic law we are going to discuss here is nothing but the Stephen Boltzmann law, which will considered as a governing law for the radiation, which will be considered as a governing law for the radiation. Now here in the Stephen Boltzmann law, we are going to consider there are two bodies. Okay, as we have discussed that one is hot body and another one is a cold body. Okay, now hot body temperature is a T1 and cold body temperature, or here body 1 temperature is a T1, body 1 temperature is a T1, whereas body 2 temperature is T2. Okay, as we have discussed that all the bodies are emitting the radiation heat in all direction uh, except 0 Kelvin temperature. So these two bodies are also emitting the heat. Okay, now this body emits the radiation towards body 2. Okay, body 1 emits the radiation towards body 2, whereas body 2 emits the radiation towards body 1. Okay, now if you are considering body 1 is T1, having the temperature T1, and body 2 is having T1 temperature T2, and T1 is greater than T2. So in this case we can say that the body 1 emits more radiation towards body 2, whereas body 2 emits less radiation towards body 1. Okay, whereas in another format we can say that body 1 receives less amount of heat by radiation, and body 1 receives less amount of heat by radiation, whereas body 2 receives more amount of heat by radiation. Okay, so this is the one sentence we can interpret in a two format. Okay, now according to the Stephen Boltzmann law, okay, according to the Stephen Boltzmann law, it stated that the emissive power of a black body is directly proportional to fourth power of its absolute temperature. Okay, the emissive power of a black body, the emissive power of a black body is directly proportional to fourth power of its absolute temperature. Okay, emissive power means what? Heat transfer rate by radiation per unit area. Okay, it is called as a emissive power. Okay, heat transfer rate by radiation per unit area is known as a emissive power. So emissive power, okay, it is, we can denote it as a Q divided by A. Okay, so in case of radiation, heat transfer rate per unit area is called as a emissive power. Remember this thing, emissive power. Whereas conduction and convection, heat transfer rate per unit area is known as a heat flux, is known as a heat flux. In case of radiation, heat transfer rate per unit area is known as a emissive power. So according to the Stephen Boltzmann law, mathematically we can interpret this particular law as emissive power is directly proportional to fourth power of a temperature. Emissive power directly proportional to fourth power of a temperature. Now here, this temperature is not only a temperature, it is not in a degree Celsius, it is in a Kelvin. Always remember, when we are dealing with the radiation point, take the temperature in a Kelvin. Okay, take the temperature in a Kelvin, because here we are dealing with the fourth power of a temperature. So there will be difference in a quantity if you take the degree Celsius instead of a Kelvin. Okay, so for that reason, here it is directly mentioned in the law only. Absolute temperature. Absolute temperature means what? Temperature in a Kelvin. Okay, absolute temperature means what? Temperature in a Kelvin. So that we can say that emissive power, that is Q by A, is directly proportional to fourth power of a absolute temperature. Okay, or T raised to 4. Okay, now this is the mathematical statement of Fourier's law. Now we have to normalize this particular statement by introducing the constant, now we are discussing about these two bodies. Okay, we are discussing about these two bodies. Both the bodies are emitting the heat, that is this particular body emitting the heat by radiation towards this body, and that amount of heat is nothing but a Q1, and this particular body emits the heat towards body 1, and that amount is nothing but a Q2. Now net amount of a heat interaction between these two particular bodies can be written as, okay, net amount of a heat interaction between these two bodies can be written as Q is equal to F sigma multiply by A into bracket T1 raised to 4 minus T2 raised to 4. Okay, this will be the net amount of heat exchange between these two particular bodies. Okay, so T1 is the temperature of a first body, T2 is the temperature of a second body. Okay, now here the two constant we have introduced to normalize the equation. Here two constants are introduced to normalize the equation of a Stefan Boltzmann. Okay, so that is nothing but F and sigma. Okay, F and sigma, where this particular F is called as a factor depends on a geometry and surface properties. It is also called as a geometry factor, okay, or a G factor. Okay, so F is factor depends on a geometry and surface properties of that particular material. Okay, then sigma, we know that this particular constant sigma is called as a Stefan Boltzmann constant. Sigma is called as a Stefan Boltzmann constant, and its value is 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. Its unit is watt per meter square Kelvin raised to 4. Both the things are important about this particular constant, its value also and its unit also. Okay, remember thing, this value also and unit also. Okay, so Stefan Boltzmann constant unit is 5.67 into 10 raised to minus 8, and its unit is watt per meter square Kelvin raised to 4. Okay, where A is the area which will be in a meter square, and T1 and T2 are the temperatures in a degree Kelvin, where T1 and T2 are the temperatures in a degree Kelvin. Okay, getting everyone? Now further we have to find out the resistance for the heat flow for radiation. Okay, so radiation heat transfer resistance. Okay, resistance for the radiation heat transfer, that we need to determine. Okay, so first of all, we know that I is analogous to Q, and dV is analogous to temperature difference TT, dt, that is T1 minus T2. So for that purpose, we have to expand this particular T1 raised to 4 and T2 raised to 4. Okay, we have to expand this T1 raised to 4 minus T2 raised to 4. So T1 raised to 4 minus T2 raised to 4 will be expanded in this manner: T1 square minus T2 square multiply by T1 square plus T2 square. Okay, further expansion will be about the T1 square minus T2 square. Okay, so we know the one mathematical law that A1 square minus A square minus B square will be equal to A plus B multiply by A minus B. Okay, in a similar fashion, we have expanded this T1 raised to 4 minus T2 raised to 4, and which will be equal to, expansion will be equal to T1 square minus T2 square multiply by T1 square plus T2 square. Okay, once again we have to expand this T1 square minus T2 square, and it will be T1 minus T2 multiply by T1 plus T2, and remaining part as it is, that is T1 square plus T2 square. Remaining part as it is T1 square plus T2 square. Getting everyone? How we have expanded this particular T1 minus T2 square, T1 raised to 4 minus T2 raised to 4. Okay, so first of all we have to expand this in this particular format, and then T1 square minus T2 square we have expanded once again. Okay, getting everyone? Getting everyone? Because we know that according to Ohm's law, I is equal to dV divided by R. Okay, and I is analogous to Q, and dV is analogous to T1 minus T2, and further remaining part we have to transfer to denominator side. Further remaining part we have to transfer to the denominator side, and through that transformation we will get the resistance for the heat transfer for radiation. Okay, that will be the thermal resistance for the radiation. Okay, so further we have put up this equation in this particular format. Okay, so just we have keeping T1 minus T2 on the numerator side, remaining part in this particular equation, whatever the remaining part is there, we have shifted to the denominator side. We have shifted that particular remaining part to the denominator side, and we will get the equation as Q is equal to T1 minus T2 whole divided by 1 upon into bracket F sigma A multiply by into bracket T1 plus T2 bracket complete into another bracket T1 square plus T2 square whole bracket complete. Okay, where this particular denominator is radiation thermal resistance. Okay, so RTH radiation, we can give the significance for this particular denominator, and where this RTH radiation will be equal to 1 divided by into bracket F sigma multiply by A into bracket T1 plus T2 multiply by into another bracket T1 square plus T2 square whole bracket complete. Okay, and the further we have to draw the electrical circuit for the radiation heat exchange. So as we have discussed, there are two bodies. One is maintained at a T1 temperature, whereas the other body is maintained at a T2 temperature. In a similar fashion, here also we have discussed about this, that one body T1 temperature, another body T2 temperature. Okay, and the T1 temperature is greater than the T2, so that the net heat transformation will be happen from T1 body to, or body 1 to body 2, that is from temperature 1 to temperature 2. So heat flow direction we have to show from T1 to T2. Okay, T1 to T2, and for this heat transfer, the resistance will be shown as a resistance symbol, and that will be equal to 1 divided by into bracket F sigma A multiply by T1 plus T2 into another bracket T1 square plus T2 square, T1 square plus T2 square. Getting everyone? Getting everyone? Is there any question, any doubt? Right. 3 into 10 raised to 8 meter per second. 3 into 10 raised to 8 meter per second. That will be the speed of light. Okay. So note down the points. Radiation. 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 If you have any doubt, any question, you can ask. Give heading as a radiation. This is the third mode of a heat transfer, that is radiation. That was the first point. All the bodies above the temperature of a 0 Kelvin, all the bodies above the temperature of a 0 Kelvin, all the bodies above the temperature of a 0 Kelvin emit radiation. All the bodies above the temperature of a 0 Kelvin emit radiation. Second point, radiation heat is thought of an electromagnetic waves. Radiation heat is thought of an electromagnetic waves. Radiation heat is thought of an electromagnetic waves. So third point, so transfer of heat by radiation. So transfer of heat by radiation occurs transfer of heat by radiation occurs because because Hot body emits more heat. Hot body emits more heat. Hot body emits more heat than it receives. Hot body emits more heat than it receives. And and cold body receives and cold body receives more heat more heat than it emits. Cold body receives more heat than it emits. Full stop. Then fourth one, requires no medium requires no medium requires no medium for propagation. Requires no medium for propagation for propagation for propagation for propagation will pass through vacuum will pass through vacuum will pass through vacuum will pass through vacuum. It travels with velocity of light. It travels with velocity of light. Note down the velocity of light, 3 into 10 raised to 8 meter per second. 3 into 10 raised to 8 meter per second. Okay, the next point, like light, like light, like light, it shows it shows it shows interference interference interference. Okay, I think electricity problem. uh, I will dictate, you please write down. Okay, like light, it shows interference, diffraction, 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 and polarization, and polarization, and polarization, etc., etc. Radiant heat can be radiant heat can be reflected. Radiant heat can be reflected from the surface from the surface and obeys. Radiant heat can be reflected from the surface and obeys the ordinary laws of reflection and obeys the ordinary laws of reflection. Okay, so this is about the radiation. So next point, write down the Stefan Boltzmann law. Stefan Boltzmann law. Stefan Boltzmann law. Stefan Boltzmann law. So in that, write down Stefan Boltzmann law. Yes, electricity problem. Ashley, because of electricity problem, the screen is not visible. Okay, so we will after writing this particular law, we will stop here only. Okay, so please note down the law only. Stephen Boltzmann law. Stephen Boltzmann law. The law states that the law states that the law states that the emissive power of a black body. The law states that the emissive power of a black body. The emissive power of a black body is directly proportional to is directly proportional to the emissive power of a black body is directly proportional to fourth power of fourth power of fourth power of its absolute temperature. Fourth power of its absolute temperature. Okay, so further thing we will dictate tomorrow, and we will discuss tomorrow, and I will dictate the write-up part also in the tomorrow's lecture. So we will stop here. You can put up your roll numbers in the chat box, and you can leave this particular meeting.
समर्थ. ए समर्थ. Sam,